Hi, thanks for watching. I'm Yuchong from Huazhong University of Science and Technology. I'm excited to be here to introduce our work. This is a joint work with Inspire. First of all, we will give some background information of high-density storage server. High-density storage server, or HDSS for short, it is a storage server which packs a large number of disks together. For example, a Dell PowerEdge server can support up to 192 drives. HDSS has been often deployed in modern data centers to reduce physical space by packing many disks into a single server. In this way, it can achieve cooling and management cost savings. Since an HDSS is composed of many disks, it is critical to provide availability guarantees against disk failures. To maintain availability, ErasureCoding is a widely adopted redundancy technique. Compared to replication, ErasureCoding needs less storage cost while maintaining the same availability. Take Reed-Solomon codes, one of the most popular Erasure codes, for example. First, the original data is divided into k data chunks. Second, these data chunks are encoded into k plus m coded chunks, including k original data chunks and m parent chunks. All these k plus m chunks form a stripe. IS codes are MDS code, which means that any chunk can be reconstructed by any k surviving chunks of its stripe. The conventional RAID-based storage server repels a failed chunk by reading k available chunks of the stripe from k disks at a time into memory, which we call full stripe repel, or FSR for short. FSR will be the baseline algorithm in our work. The failed chunk can be reconstructed through a linear addition of the k surviving chunks. ErasureCoding has a challenging repel problem. In this work, our ErasureCoded repel problem is a little different from that in traditional distributed storage system. For distributed storage system, when repairing a chunk, the k surviving chunk will be transferred, and that will cause the congesting network. So many ErasureCoded state-of-the-art repel schemes focus on how to perform repel with limited network resources. Many of them aim to trade sufficient computation and memory resources for limited network resources to repel a lost chunk efficiently. In contrast, for our work in HDSS, because of the parallel property of the RAID architecture, multiple full-stripe repels will be performed at the same time, which will incur memory computation. And we surveyed the ErasureCoding state-of-the-art studies that improve repel performance in parallel for distributed storage system here. We clarified them into two types of parallelism. The first one is the intra-stripe parallelism. The linearity of ErasureCoded repel enables the single chunk repel to be performed in parallel within its stripe. So we call it intra-stripe parallelism. Many state-of-the-art are based on this parallelism, such as PPR, RP, PPT, and so on. The second one is the inter-stripe parallelism. Different server nodes can transfer data simultaneously, so multiple single chunk repels can be performed in parallel, which we call inter-stripe parallelism for distributed storage. Recent studies such as EC-Wide and Repel Boost are based on this parallelism. All the above two parallelism are based on the repair traffic rescheduling by paralleling the repair operation over distributed storage servers. And each of these servers use its memory to do partial repair of the stripe. So we call it partial stripe repair, or PSR for short. However, the current PSR schemes are only designed for distributed storage so far. And for HDSS, we only use the current scheme only use FSR, and no study has focused on how to exploit PSR in HDSS. And in HDSS, the Erasure-Coded repair problem, as we stated above, is about a memory computation problem. And for FSR, multiple simultaneous FSR stripes will compete for memory, so it will impair the disk repair performance. So in this paper, the major challenge is how to take full advantages of PSR in HDSS to exploit intra-stripe and inter-stripe parallelisms. Before introducing our motivation, we first give some definitions. Let's begin with the ACWT. Disks often have different transfer speed because different disks may be under different workloads. Chunks on faster disks will be read into memory before the chunks on the slow disks. So the faster chunks have to wait for the slow chunks, because in FSR, the repair operation will not happen until all the surviving K chunks are read into memory. The time interval during a faster chunk waiting for the slow chunk is its waiting time. We define the average of all chunks waiting time as ACWT. Another definition is the total repair runs. Some chunks are read into memory as a repair run, and the number of runs it takes to repair a stripe as the total repair run of this stripe. We can see that all stripes in FSR only use one repair run by default. Here, we introduce a motivating example to show our main idea. Assume that there are two stripes to be repaired, and each chunk's read time is listed in the table. And on the top of the figure, you can see this in the paper. If we adopted the FSR, figure A shows that the total time of repairing two lost chunks of the failed disk is 7 units, and the ACWT is equal to 1.625, which can be calculated in this figure, based on this figure. In contrast, figure B shows the idea of our method. We read two chunks of each stripe into memory at a time instead of reading all of them like FSR. Then compared to FSR, the total transfer time of PSR is reduced to 5, and ACWT of PSR is reduced to 0.375. Since that, for all the 8 chunks, only 2 chunks, C3 and C7, need to wait 1 or 2 time unit. So the waiting time is very small. And in this paper, our contributions as follows. We analyzed intra-stripe and inter-stripe parallelisms and observed that these two parallelisms mutually restrict each other, and both of them will affect single disk repair in HDSS. We designed 3 algorithms to accelerate the disk repair performance. We designed a cooperative multi-disk repair algorithm to enhance multi-disk repair, And in evaluation, we see that our algorithms really work. Sorry. And then we introduce our uh, three observations. First, there is a mutually restrictive relationship between intrastripe and interstripe parallelisms. For example, assume that the memory capacity is 4 chunks and a stripe is composed of 4 chunks. If we use FSR and the intrastripe parallelism degree is 4 and the interstripe parallelism is degree is 1. However, if we adopt PSR, we read 2 chunks instead of 4 chunks into memory in every time unit, and the memory can deal with 2 stripes at the same time. In other words, the intrastripe and interstripe parallelism degrees are both 2. So intrastripe parallelism and the interstripe parallelism are mutually restricted. Second, the intrastripe parallelism and ACWT are positively correlated. The reason is that a higher intrastripe parallelism indicate that more chunks of a stripe will be read into memory at times, so more chunks have to wait for the slow chunks of the stripe, then increase the ACWT. At the same time, interstripe parallelism and the total repair runs are positively correlated, as an increase in the total repair runs affect a single chunk repair and so influence the repair time of a single disk. In summary, we need to consider both parallelisms together instead of setting one of them to the maximum. So we still need to design more sophisticated algorithm to exploit these two parallelisms. So we designed 3 algorithms to improve disk repair by taking full advantage of PSR. First, we introduce an active preliminary algorithm first. The objective of this algorithm is to obtain a reasonable intrastripe and interstripe parallelism that can minimize the total transfer time based on the input L. And L is a 2-dimensional array element in the ith row, and the jth column represent the read time of the jth chunk of the ith stripe. The word active means that we obtain the L by actively testing the disk transfer speed actively. We divide the chunk size by the disk transfer speed to get the read time of the chunks. Because of the input L is a 2-dimensional array, so the output is a value, so we use a twice dimensionality reduction algorithm to simulate the transfer process and get the final result. But the preliminary active PSR is very time consuming. So that is why we design another active algorithm to reduce the time complexity. We state that the essential reason for slow repair is that the slow chunks drag down the fast chunks. So the main idea here is we try not to let the fast chunks to be encumbered by the slower chunks. In the first step, we design a fast and slower pointers algorithm. It counts the number of slower chunks of each stripe and move the slower chunks together, and then it gets the maximum number of slower chunks of all stripes as the intrastripe parallelism. In this way, we can group the slower chunks together and read them first. That's why this algorithm is called the active slow first PSR. And we said the time complexity is lower than the first one. And the above 2 algorithms have to obtain the input L through active testing, it will occupy the CPU and the memory resources a lot. So it is necessary for some CPU or memory constrained cases to design a repair problem that does not have to actively detect the current disk transfer speed. So we designed the passive PSR. Passive PSR adopts FSR first by default. When the repair is performed, we set a timer for each chunk. When the time to read the chunk exceeds a certain threshold, we mark the disk as slow. If slow disks are encountered while repairing a stripe, we first read all the chunks on the slow disk to memory and then read other chunks in the second time. So the time complexity of passive PSR is the same as the active slower first algorithm, but it has much less CPU or memory consumption. When multiple disks are failed, traditional method simply repairs each failed disk individually until all the failed disks are reconstructed. There will be some unnecessary redundant computations and disk I/O, so we proposed a cooperative multi-disk repair algorithm to enhance the multi-disk failure repair. First, we create a stripe set for each failed disk. The stripe set stores the connection of stripes kept on each failed disk. Then we join all stripes set together and remove the duplicate element. Then we had the minimal number of stripes that need to be repaired to construct all the failed disks. Then we used HD PSR to repair each of the stripes and write back the failed chunks to backup disks respectively. Well, let's check our system's HD PSR's performance. As you can see, our system HD PSR reduces the overall single disk repair time by up to around 70% compared to FSR. And the active slower first PSR reduces the algorithm running time by up to around 100% compared to active preliminary PSR. On the other hand, our proposed HD PSR also outperforms FSR when the chunk size ranging from 8 MB to 256 MB. Meanwhile, HD PSR with the cooperative multi-disk repair reduces the overall multi-disk repair time by up to around 50% compared to that without the cooperative multi-disk repair scheme. At last, we make a summary here. In this paper, we propose the concept of intra-stripe parallelism and industrial parallelism, and gives 3 observations and analysis of these 2 parallelisms. We designed 3 practical algorithms to significantly reduce the single disk repair time compared to FSR, and a cooperative multi-disk repair algorithm to enhance the multi-disk repair. Also, our evaluations show the algorithm's efficiency. By the way, our source code is available on GitHub now. That's all for our work. Thanks for watching.